Okay. Ladies and gentlemen, good afternoon and welcome to my presentation. My name is Dr. Mohammed Maqsood and I'm a postdoc researcher at Maastricht University. Today I will talk about the bio-based textile opportunities that our institute can offer to the textile industries and textile institutes in the Netherlands and also throughout Europe. First, I will start with a brief introduction of our institute because not everybody knows our institute. Therefore, I will start with what we are doing, what are our expertise, and what we can offer to the textile industry. Then I will talk about the expertise of our research group, then what are the projects we are involved in with the textile industry, and later how industry can collaborate with us in different projects. First, what is AMIBM? So AMIBM stands for Aachen-Maastricht Institute for Biobased Materials. It is an institute of Maastricht University, and which is located in Brightlands Camelot campus in Geleen. So Brightlands Camelot campus is a huge chemical site, but we are located in this building in Center Court and also in Building 1. As you can see in the map, although we are located in the Netherlands, but we are very close to German border and about 30 kilometers away from Aachen and about 25 kilometers away from Maastricht University. So we are in kind of in between, between Maastricht University and RWTH Aachen University. Now to talk about our research group, Professor Gunazaide is our head of the department. And at the moment, we have 6 PhDs in our research group and 1 postdoc researcher. And some of the PhDs are working on bio-based polymers, some are working on bio-based additives, some are working on flame retardants, some are on colorants, but some are on conventional textiles. Now, the core competencies of our research groups can be classified into 3 different categories. Number 1 is fiber spinning, number 2, additives, and number 3, aerogels. When we talk about fiber spinning, we have state-of-the-art labs in our institute, starting from lab scale to pilot scale and then to industrial scales. Because not many institutes in the Netherlands have production facilities, but we do have not only at pilot scale, but also at the production scale that I will show you in my slides next. So we do have facilities related to wet spinning as well as melt spinning. So if we take a look on wet spinning, we start with the lab scale. We can process the polymer with as minimum quantity of 5 milliliter of the solution. Here we can test the spinnability of the polymer. If the polymer is spinnable, then we upgrade it to pilot scale, where we can test the spinnability up to 200 meter per minute winding speed. But then in the technical scale line, where we do projects with the industry, we can produce non-woven structure, we can produce medical textiles, face masks, surgical gowns. These are the projects that we are currently doing with the textile industry in medical sector. When we talk about melt spinning, we also have state-of-the-art labs classifying into 3 different categories: lab scale, pilot scale, and technical scale. In lab scale, we can only test the spinnability of the polymer, and then we can upscale it to pilot scale, where we have capacity to run it up to 2,000 meters per minute. But that's not only the facility we have. If we talk about the technical scale, we can process up to 10 kilogram per hour. That's the capacity we have at our technical scale line melt spinning machine, and we can produce yarn up to 5,000 meters per minute. In melt spinning, not only wet spinning to produce filaments, but we can also produce staple fiber lines. And a company, you can see the logo IFG Azota, that's a company based in Austria. And recently we have bought a machine together with Maastricht University and IFG Azota. And this machine can produce staple fibers, and the capacity of this machine is 80 kilogram per hour. So this machine can really produce quantity in bulk, and if a customer or a company is interested to produce staple fibers, we can produce that in Austria because this machine is bought together with Maastricht University funding and together with IFG Azota. Later I will show you also the video of this machine where you can have a better look. Now to the industry funded projects or public funded projects we are involved in as institute. BIOTEX FIELDLAB is one of the projects in which I worked in my PhD. And the aim of this project was to develop textile products from biopolymers. And the people you have already seen me in the booth, I have displayed some of the demonstrators that we have developed in this project. Well, the aim of this project was to produce textile demonstrators, but another objective was to build a field lab in Maastricht University, because in Netherlands, we don't have many institutes which have state-of-the-art labs in textile industry or textile-related facilities. So not only we develop textiles from bio-based polymers, but we also have developed a lab consisting of from production to testing and to also we can also label different products. We have certified labs. These are the real demonstrators that we have developed in this project. As you can see, carpet from PLA, Douai from PLA. So Douai is a demonstrator that we developed, a well-known company in Netherlands, Opping. Maybe you heard the name. We have developed this, and carpet with a company, Deso. Socks from PLA with a company, Star Sock. And then non-woven backing with a company, Lowe and Bonner. And these are the demonstrators I have displayed here in my table, and I think most of you have already seen that. But in case if somebody have missed this, you can always contact me to have more discussion about it. Since we have time limitations, I have selected only one product just to show you how we developed that. As you can see from the title, one material carpet. And what do we mean by one material carpet? Because we all know carpet is a multi-component structure. Because if you look a carpet, you can see on the face there is a tufting yarn from one polymer, then non-woven backing from another polymer, then we have to glue it from another. But here in this case, we have developed a carpet only from one polymer. So face yarn is from PLA, then we have a non-woven backing also from PLA, then the glue also from PLA. So the idea was, when we produce a carpet from one material, it is easy to recycle, because we have seen a lot of presentations and also people were talking about recycling. It's much difficult to recycle a product when it's made from multi-components. But if it's made from one component, it's much easier to recycle it, not chemically, but also mechanically. So that was the main objective of producing a carpet. PLA is bio-based, biodegradable, but we have also enhanced the functionality in terms of we can also recycle it. So all three purposes were met in this product. Then how we produce the non-woven backing from PLA. We had the luxury of having PLA in different grades. Corbion is a supplier of PLA in our project, and they developed two different grades, having low melting PLA and high melting PLA. And when you have two different grades, you can process it into bi-component yarn. And what do we mean by bi-component yarn? In one single yarn, there's a sheath material and a core material. In the sheath material, we had low melting PLA. In core material, we had high melting PLA. And what the purpose of that? Because when we thermally processed it, the low melting PLA sticks with the high melting PLA, and then we can produce a composite structure only from one polymer. Because we all know composite structure is a structure which is mainly produced from different polymers or different materials. But in this case, we can say it's a composite, non-woven, but made from one polymer. Then to another public funded project. The name of this project is Beautifully Bio-Based Fibers. And in this project, we are producing not only the yarn from bio-based material, but also the colorants. So you can see the dyes. Normally with dispersed dyes, people are using to dye the fabric or the yarn or many other techniques. But in this case, we use the technique dope dyeing, and the colors were also from bio-based materials, not only the base yarn, but the color itself. So my colleague, Naveen Balakrishnan, is doing PhD in this topic, and he developed bio-based colorants from bio-based building blocks, which were obtained from flowers and plants. So we developed the building blocks from flowers and plants, and then we stabilized them with nano additives to make it stable to be used in melt extrusion process. And then we developed yarn, which is of multicolor or for different applications. The next project name is BB100. This is a European funded project. In this project, the aim was not only produce textiles from PLA, but also the additives that we use inside should also be bio-based. So my colleague Stephen Hermans is working in this project. He's doing PhD. In this project, we have two other partners, Evans, Hawk School, And then we have Textile and AMIBM. So AMIBM part is to develop yarns. Then with Avans Hawk School and Textile, we are developing bio-based additives. And then at the end of this project, we will develop textile demonstrators. But this project is still going on. The demonstrators are in the preparation phase. Maybe next year when we come here, we will bring those products with us and we'll show you not only the textile itself from bio-based, but the additives that we use inside are also produced from bio-based resources. Now, just to give you one example what bio-based additives means. So here we produce a flame-retardant fabric, and in this case, the additives used are bio-based. Main polymer is polylactic acid, and the technique that we used is called intumescent technique. And what does it mean? It means when a material is burned, a char layer is developed on its surface. Here you can see a polymer, when it is burned, a char layer is built. And why we need a char layer? We all know oxygen is the main component in order to take place fire. So if a char is built up, this layer will not allow the oxygen to go inside. And we all know if oxygen is removed from the burning site, the fire will stop. The other objective does not allow the smoke to go outside, because sometimes smoke is even more toxic than the fire itself. So that's why the other objective is to not allow the smoke to go outside in case if a fabric is caught by fire. The third objective is it reduces the heat of combustion, and heat of combustion is required to further propagate the fire. So in this technique, we not only stop the fire, but we also don't allow the smoke to go into the environment, because during inhaling it can further cause injuries, or even a person can die if he can inhale smoke. And the third is it also reduces the heat of combustion, does not allow the heat to further propagate the fire. So this is one technique we are working in bio-based additives to produce textiles which are flame retardant, and all the additives are bio-based. Now, in my final slide, I will talk about the industry collaboration that we can offer to the textile industry. These two equipments or the machines that you can see in this slide, we call it a unique infrastructure. And why unique infrastructure? Because you might see lab scale or pilot scale machines in different institutes or even in industry in Netherlands, but not many have the luxury to have production facilities, but we as institute, we do have. So I would like to show you the video of our labs and the staple force line that we have. So that was the staple fiber line, where we can produce at industrial scale up to 80 kilogram per hour. So that's the production capacity we have at the moment. Well, thank you very much for your kind attention. If you have any questions, yeah, please feel free to ask.